live? Sahil?
Checking.
It
Well, we
doesn't.
are live, but usually takes a little bit of time.
Yeah, it seems like internet is a little unstable right now.
Everyone's been saying that today.
Is it reasonable?
Are you reasonable?
Okay, we're live.
Okay. Okay, hopefully the listener will tell us if there's a sound issue. There shouldn't be. But anyway, uh, hello everyone. Welcome to Corecast. I am your host, Tim.
And I'm Mikey.
And I'm Sile. Welcome everybody to a brand new exciting episode of Courtcast. If you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions in the episode, and we'll get to it. And also in addition to that, we're in the process of making shorts. So if you have any ideas for shorts, do let us know in the episode. We'll put that into consideration. So without further ado, let's get to it. Tim and Mikey, this is an interesting experiment that that we came across regarding dark matter and how and in our title, Dark Matter just got darker. It's very ominous sounding, and we'll definitely cover that. So I think it might be helpful to maybe start off and explain like very briefly what is dark matter, high level bullet points of this experiment, like kind of the end of what we'll get to, like what did they discover, and then how do we then we'll kind of lay the groundwork and continue from there. So I guess Mikey, I'm going to point to you. What is dark matter in like one or two sentences?
Wow, one or two sentences. Dark matter.
Yeah,
So, um,
and we'll go into detail later. So I just the high level.
yeah, okay, yeah.
Yeah.
When you look out into space and you look at the stars, you see a huge amount of like invisible junk that is pulling on galaxies and like sucking everything in. And it's like this everything is moving according to this like, and the only way we can see it is by how it pulls on things with gravity. And uh it just looks like there's a bunch of junk out there. Like, what is this junk?
Yeah. And then Tim, I'm gonna defer to you. What is the significance of this experiment? Just kind of jumping to the punchline.
Yeah, so basically we know that 80% of the matter in the universe, we don't know what it is. It's dark, it cannot be seen. So the first thing you want to ask is it really dark? Maybe we can see it in the lab. So what we're talking about is the Lux Zeppelin experiment. It's one of many what we call direct detection experiment. It's basically the most straightforward way to find dark matter. If there's a dark matter, maybe we can capture its hints in a lab. And that's what we're talking about. Just literally seeing dark matter on Earth. If dark matter is not as dark as we thought, then we might be able to find it.
Gotcha. So this experiment was basically a way of seeing if we can detect what dark matter is, and hopefully it's not as dark as we thought. Is that the gist of the experiment?
Yep. That's roughly
You
right.
might
Okay.
ask, what does it mean to be dark?
That was my next question.
Okay. Yeah. Yeah, like so I think it's worth stressing at this point that like when we say dark, um, like a lot of people think that light is just something we use to see, like with our vision. It is true that the reason I can see this table is because particles of light are scattering off of the lamp onto the table into my eyes. Um, and yeah, that's a big part of the role of what light plays in our lives is helping us see. But it's also true that the reason my hand doesn't go through the desk is because when my hand gets close to the desk and my hand start emitting particles of light at each other furiously that oppose and resist my hand going through this. So um, light is the reason why um, like tangible objects encounter resistance. Um, if something is dark and doesn't interact with light at all, it could be literally just as dense as you. You could be literally like a person, like a dark person, and you just pass right through me because there's no electromagnetic interactions between me and you. Then we just pass through each other. Metapart statistics about like how matter is mostly empty space, and how the atom was the size of a football field, the nucleus would be the size of a sand speck. So you literally just imagine these things passing through with no interaction. It would just go right through each other. So
Yeah,
that's what it means to be dark.
Yeah,
Go ahead, Tim.
let me just add that, for most ordinary matter, like my hand, for example, anytime you do anything with your hand, you're actually emitting light. Most of that light might not be visible. They might be infrared. And if I just wave it around this way, it might be very, very low energy light. But nevertheless, light is emitted because my hand contains electrons and protons, and they have electromagnetic charges. And like our everyday lives, chemistry, all depend on electromagnetic interaction. So when we say dark matter is dark, it really means that dark matter doesn't have that kind of interaction. Like if I, like and it is because of, like Mikey said, it's because of electromagnetic interactions that one of my hands cannot pass through the other, right? But the same cannot be said about dark matter, because if dark matter really is not dark, we would have seen it, first of all. Maybe we would have seen it with our naked eyes even. We would have felt it, maybe you put some material there, dark matter could hit it. But it's just that we haven't seen it so far. And that's what this experiment is about. How much can we say dark matter hasn't hit us or hasn't shine a light?
Mm-hmm. Yeah. So I just want to touch upon what we've been talking about. So we described dark matter as dark, and that makes sense to me. That doesn't interact with light, or lack of interacting with light, or how much does it interact with light, and that determines the quote unquote darkness of it. And now you said, like, if we can't see it, can't interact with it, can't really touch it, or I guess measure it in like everyday life, how do we even know it's there? Like, why? What's kind of the point of this existence? Like, how do you know it's there, and like what's the importance of it?
Yeah, I would say there's a conventional answer that you'll find in most YouTube videos, and that's that's an answer. That's not a great answer. Most people would say, oh, because galaxies rotate in one way or another. Basically, galaxies rotate a little too fast. If you look at the visible stuff, calculate how much.
A little fast. They rotate way fast.
Yeah, way fast. Okay, way fast. Okay, but that's actually not the best evidence. The evidence is actually that the fact that we even have a universe with galaxies and structures around, it turns out that if there is no dark matter, if we just have the visible stuff is kind of very clumpy, if you think of it, like sticky. They interact too much. So if you throw a lot of visible stuff into the universe, they'll clump up, and you will actually not get structures like galaxy, which is kind of like a fuzzy spread out structure that can spin around, even though it's such a large object. It can kind of consistency spin around in that way. The structure of the universe is impossible without dark matter, it turns out. So that's actually the strongest evidence for dark matter, because people come up with all kinds of different models to get around, weasel their way around the dark matter requirement. None of them work because of the structure of the universe.
Yeah, I just feel
good, Mike.
Like everything about the evolution of the universe depends on how much stuff there is in it. And as Tim mentioned before, like this stuff, it makes up, when we measure it, it makes up 80% of the stuff. You just take away 80% of the stuff, the evolution of the universe looks radically different. And especially if you have, like, if everything is interacting, as Tim said, like all hell breaks loose with your theory of how the universe came to look like this.
Could you elaborate further on, I mean, it doesn't have to be too deep, but on the structure of the universe? Because, I mean, like, there's the galaxy rotation thing, that are rotating way faster than they should be, but it's like, if you took away dark matter and they just, let's say they rotate even slower, it's like, who cares? Like,
I thought they would rotate slower, they would fly apart.
Oh,
So
they'd
dark
fly
matter is
apart.
like
Okay.
dark matter is like the glue that holds everything together. Without it, like,
Mhm.
what you'd have is you'd have like a mix of like things like galaxies would fly apart and other things would clump into over densities. It's the density distribution
Mhm.
would look totally different. This evolution, in order to get the universe to look like the way it is now, you need this kind of invisible, like it's like glue. I don't know. It's like glue. Literally, it determines the large scale structure of the universe, like the superstructures, like clumps of galaxies, the way they form these filaments. People might have seen pictures of it. Um,
Mhm.
yeah, so that's all determined by the dark matter distribution.
Yeah, and let me just
Got
add. Let me just add. I don't want to go into too much details, but it's much beyond just galaxy. It has to do with how multiple galaxies can the statistic of how these galaxies are distributed. Because in the beginning of the Big Bang, the universe is expanding, and the dark matter component kind of modulate the amount of expansion. If you have just a little too much, the expansion will slow down a little too fast. Then the galaxy will be a little too close, and stuff will happen. And if you have a little,
Mm.
if you have a little, yeah. So if you have a little too much dark matter, it might, the expansion will slow down a little too fast. If you have not enough, the expansion might go a little too fast. So we have very strong evidence that we have this Goldilocks amount of dark matter just right to get the universe dialed in exactly the way we are right now. So that is, if you talk to anybody with alternative theories about dark matter, they just couldn't get that right. I mean, this is just the strongest evidence of dark matter.
That's funny. It does
Got-
almost seem like someone added like 2.5 liters of like corn oil into like a recipe, right? To make it just right.
Yeah. So okay. So that makes sense to me. That not only the galaxy rotation curves, but as well as like the structure of the universe, how far galaxies are spread apart, and other things, give strong evidence for dark matter. So I guess like, can we maybe cover historically what people thought dark matter is, and then maybe the most optimistic model of dark matter, and kind of how the understanding has evolved, and where this experiment fits in. I guess Tim, I'll start with you.
I think historically we have to understand some context. I think back then people realized there's dark matter, and then we also know that there's one type of particle that we already know and exists, kind of feels like dark matter, and that's called neutrino. So the sun, I think, is producing a crap ton of neutrinos. I think every second there's like maybe, is it some millions of neutrinos passing your hand? I forgot the numbers. A lot. Okay.
Something like that, yeah.
Yeah. And so that's kind of like dark matter. Like there are particles called neutrinos that has mass passing through your hand every single second and passing through the earth. And you could actually go measure it. People have to build solar telescope to see occasionally these neutrinos could hit an instrument and leave basically like a camera, a neutrino camera. Sometimes you can take like a really grainy picture of it.
Wait, tell them real quick about Ice Cube, just super quick.
Oh yeah, there's also they effectively made one of the largest neutrino camera in the world, and using ice itself. And the best place to find ice is the South Pole, and so it's very interesting. They use the ice as an instrument, but let's not go into details. But anyway,
no, but the idea is that like neutrinos interact with matter so rarely, but like once in like in a blue moon, you might get a perfect hit with a neutrino off a nucleus or something, and then so the more material you have, the more likely you are to see that. So their size really matters, right? So here we're some neutrinos, they're dark, but they're not totally dark. So once in a while they do bounce off of you know a nucleus of something that we know about.
yeah,
Yeah.
yeah, and the first
sorry.
and the first question people ask is like, is neutrino dark matter? Isn't that the answer?
Yeah.
It turns out it's not enough. Neutrino is very little. You can calculate it, and also neutrino is a little like almost like too light, moving too fast, too light.
It's either too light or too heavy.
Yeah. So in any case, neutrino doesn't fit the bill. But look, if you see that the world has neutrinos and it's just passing right through us all the time, it's not crazy to think that maybe neutrinos has some cousins just hanging out. and we just haven't seen it yet. So that's a very natural hypothesis, and this hypothesis has been coined as the WIMP hypothesis.
No, well, no, that what you just said is the right-handed neutrino thing.
Sorry.
Well, the idea you just described is closer to the right-handed neutrino.
Well, yeah, I
Dark matter.
don't. Yeah, I mean, it's not technically the same, but the same line of thought.
No, you said partner of the neutrino. Oh, wait, oh, okay. They're both similar. Sorry. Yeah, there's a lot of ideas like this.
Like cousins of neutrinos, but darker. Okay, let's put it that way. So
okay. So yeah, go ahead. Tim.
Yeah, and I also want to add and heavier, a little more massive, a little chunkier, chubbier, whatever you call it, a little. Probably not a good idea to anthropomorphize it, but you know.
A little Higgsier. A little Higgsier. No. These wouldn't be Higgs. Never mind. Crash that.
Okay. I was about to call you out on that, Mikey, but
No,
you caught yourself.
Backtracking.
The crowd was about to unleash their wrath on you for that.
No, I'm sure that's not totally wrong.
Yeah. So okay. So I guess actually one interesting thing, I don't remember you said this, Tim, or Mikey said this, but either they're too light or they're too heavy. Why can't you have something like in the middle, like a Goldilocks, like dark matter kind of thing? Like, why does it need to be on the extremes?
I wouldn't say that. We actually don't know what the mass of dark matter is. The possibility can actually be very, very, very light, even lighter than neutrino, but it cannot be like neutrino. Or it can be very, very, very heavy. It can be so heavy that it could be like planet size heavy, possibly. So the possibility is wild, I would say. But if you modify the mass of the dark matter, you also have to make it work with our universe in different ways. So like if you change the mass, you might have to modify the way dark matter interact with other stuff. So I would say the Goldilocks mass would be like, if you imagine it's a little bit like the neutrino, but heavier, then it will be somewhere around the mass of the Higgs boson. At least that's what people thought. I guess it's more like a psychological Goldilocks zone. You know, people really thought that dark matter will be kind of like the Higgs boson, except very, very, very dark.
That would be the fantasy for someone who really wanted to win the Nobel Prize, right?
Yeah. So we mentioned the word WIMP or WIMPs. I mean, when I think of WIMPs, I think of something that's like really weak. Typically used as like. Oh, what's up?
That's actually up.
Yeah. So I'm wondering what is the acronym? I'm assuming it's an acronym. What does it stand for, and like what is this? What's the overall like significance of it?
I think someone spent a lot of time thinking about these acronyms. It's actually pretty good. It stands for it stands for weakly interacting massive particles, and it's kind of wimpy because like even though it's very heavy. It can't do very much to you. Like it can't knock you over because it interacts so little. It just passes right through you. It can't do much to you. So I guess it's wimpy in that sense.
Yeah, but it's like beyond that, there's also like I guess the context in the name as it regards to the weak force. So everyone knows about the electromagnetic force, but as people started probing the atoms structure and stuff like that, they started noticing these forces that were weak. Like their effects were not apparent in everyday macroscopic life. One of those was the weak force, which was called the weak force because it looked weak. And the hope, and so the weak force is the force that neutrinos interact with. If a neutrino is going to scatter off of a nucleus, it's going to happen through the weak force. But because it's so weak, this happens very rarely, and that's why neutrinos pass through us, kind of like ghosts. And the hope is that, dark matter, as we've been kind of emphasizing here, that maybe dark matter passes through us like ghosts as we observe it to do, but maybe it also interacts with us a little bit, like neutrinos do, through the weak force.
Hmm.
And if such a
And
particle happens to be very heavy, then it's a weakly interacting massive particle.
so weak force is just in other words responsible for nuclear decay, essentially. Like just one of the
That's what
forces
people
that.
say, but it's
Mhm.
really just a force in the normal sense. But it's just the problem is the effect is so suppressed that you can only like particles only feel it if they get really really close to each other, which never happens in nature.
Mhm.
Yeah,
Yeah.
let me just add that the weak force is not just responsible for decay.
Mhm.
Particles can feel a repulsive or attractive force through the weak interaction. It's just a lot weaker than actual magnetism, but the weak force can attract and repel.
Okay. Okay. So let's jump into the experiment. So what was this experiment necessarily like testing for now that we've laid all the groundwork of dark matter, WIMPs, and then what were the findings? So Mikey, I'm gonna start you off since you look really eager.
No, I'll just give like a super like so this experiment is not new or novel, as far as I know. That could just be my ignorance, if I think about it more carefully. But really, like what people have been trying to do. So if dark matter is weakly interacting, meaning it passes through us like a ghost, but once in a blue moon it might knock nucleus here and there, then what do? You would want to get the densest material you could find, put it in a box, and wait for like 10 years and see if anything knocks. Um, of course, there are things we know can knock the nucleus, like neutrinos, as we just mentioned. So you have to like know exactly how many neutrinos are coming from the sun and how many are coming from other sources and subtract that. And then you see if you try to see if there's any unusual knocks um, going on in your box of dense material. These are called, they go by the name of direct detection experiments because you're literally just
Mhm.
seeing if something just happens to just knock
Yeah.
something. And so it's like the simplest stupid of all experiments. I'm not sure why this one is special. They use different materials, and as time goes, they get more and more sophisticated, and they rule out more and more
Yeah.
scenarios.
Yeah.
And this is yeah,
I can add little details on the experimental physics
yeah.
side. So the material choice is important. You have to consider first you need something very dense, but also detectable, right? Like if you have a bunch of lead, sure they're really dense, but like let's say something inside the lead got knocked off. How would you know it's in the metal, right? So what people end up doing is a lot of times they use like liquid and very stable liquid like xenon. It's like the heaviest noble gas, and because it's so heavy, the chance for it to get knocked by dark matter is higher because we believe dark matter is very very heavy. So they kind of it's easier to get heavy stuff to knock on heavy stuff, and you can also remove the noise because and also these experiments happens underground, very deep. I think this one is it in South Dakota? I don't remember. It's some
Yeah.
mine. Yeah, it's in South Dakota, very deep. I forgot the numbers, so that you don't get bombarded by cosmic rays knocking things left and right. So basically, you just have a big vat of xenon deep underground with a crap ton of sensors, you know, super cooled. That's not right. Like cool to very low temperature, and you just wait. You just wait for nothing, basically. And the more nothing you see, the better your experimental results. Of course, if you see something, then
No, the
great.
worst.
So wait, hold on. Few things. Like first of all, you mentioned neutrinos hitting things and knocking things is rare, and this should presumably be even rarer. So how do you like fish out like the actual knocking of like dark matter if it were to happen versus
Right.
like neutrinos?
Right. So the differentiating factor is that neutrinos is very light, and if you believe
Mhm.
in this WIMP paradigm, WIMP is way heavier. Like I think is it like millions and millions and times heavier. So imagine this:
Mhm.
you have a xenon nucleus, and you have a little neutrino just slightly knock it. That xenon is not gonna move very much. And if you have a
Mhm.
massive dark matter particle and the mass is comparable to probably the xenon nucleus, maybe even heavier, when it knocks it, oh man, that xenon is gonna fly, right? So the impact is just a lot larger. I mean, it's like on a highway, you know, like there's a truck sitting there. You have a little bicycle hitting the truck. Nothing's gonna happen. If you have
Wait,
another
neutrinos aren't
truck,
even the biggest background, are they? Neutrinos aren't even the biggest thing that confuses. Like,
right?
there's like, you know,
It's
when
not.
you're dealing with atoms, there's so many things that can knock an atom around. Like, I remember reading them, it's crazy.
Yeah, true. Yeah, there's like radioactive decay. Like you can have argon gas decaying underground. So they try very very hard to remove all the radioactivity. You know, but a whole bunch of experimental physics stuff that I don't have the expertise. We won't go into. But yeah, Mikey, you're right. That neutrino is not the biggest background yet. And
Yeah, oh yeah. You got to explain that, the limit.
Oh, what is this?
No, Tim, I'm sorry. Tim.
Yeah. So this is basically the crux of the result now. Like, why is this result significant? It turns out that if for radioactive background, you can always try harder. You can always wait longer, and kind of just get the experiment better, and then you can beat your background. But eventually, your experiment will not be able to improve your results anymore, because it turns out that neutrino from the sun eventually has more background than you can remove, and this is called the irreducible neutrino floor. And this is kind of the thing that experimentalists are dreading. We are about, maybe in terms of statistics, maybe a factor of 10, maybe a few more years away from that floor. 2 years maybe, something like that, okay? And when we do that, if we wait longer for nothing, it wouldn't be meaningful anymore. Because he's like, well, okay. Like, you know, you're just gonna see you're just gonna see neutrino hitting the vat of xenon. So it's like, wow. And if a dark matter does hit, you wouldn't know if it's neutrino or the dark matter. That's the crux. Basically, experimentally, we're getting close to this bound where like this line of thought just doesn't make sense anymore.
Wait, so can I just confirm, make sure I understand this, because you know more about this than me? Like, so this is because, like, you know, neutrinos most of the time it's a soft hit because they're light, but once in a while, right, if you wait long enough, there's going to be a very highly energetic neutrino that's going to hit it in a way that could resemble dark matter. Is that?
Yeah, exactly. So, but it's not. That's not to say that it's completely hopeless. I mean, experimentally, there are tricks you can play, but like, for example, when we are closer to the sun, there will be no more neutrinos, and we're away from the sun, there's less neutrino. This is called modulation. You know, when neutrinos hit the material, it goes up and down, up and down. The problem is things like that. Well, things like that could actually happen with dark matter as well. But you know, you can play this game with statistics, but this experiment gets so much harder. Basically,
it's not looking good.
Yeah, it's not looking good. The experiment gets so much harder that probably I imagine a lot of people will give up after we reach the neutrino floor.
So what you're saying is, like, even if you were to, let's say, increase the size of, I don't know, the material, amount of space it covers, wait even longer, you just try as hard as you can, there will reach a point where the I guess like the events of high energetic neutrinos hitting the material and you know, will be significant enough that you won't be able to tell whether it's a dark matter particle or a neutrino that actually hit the thing, high energetic neutrino. Is that right?
Basically.
And we're close to that point now. We're like epically close to that point, and it's just looking really sad.
I see. That is most unfortunate. So I guess, like,
this is like an experimental program that has been running for, I don't know, 20, 30 years.
But look, I don't think we should be that pessimistic. I know that it's sad that we haven't found what dark matter is yet, but like, that's what research is about. We don't know whether we're gonna find it or not. That's why it's interesting. I would say that sure, it makes state life difficult, but like, it's also not too surprising, I guess.
Sounds like something you say at a funeral.
So this is so pessimistic that you become optimistic, Tim. So it seems like I mean we've already made kind of a strong position by the thumbnail of this video putting a tombstone.
Did you
So
listen to the
yeah, so I guess like what what does this mean for dark matter? Like what I guess where do we go from here if it's not, if this we eventually reach the limit and we find like nothing or it becomes impossible to really tell.
Axion?
So
Uh actually wait, before we talk about what is like I guess like newer things that people have
Well,
proposed
that could be a
beyond
whole
WIMPs.
other episode.
Yeah, but I wanted to ask like, what if it is actually the case that you can't distinguish between neutrinos and WIMPs? Like, what if dark matter is a WIMP, but you just cannot distinguish between that and neutrinos? Like, what what then?
There are bounds on like the allowed like density. Like yeah, Tim would have more
yeah, yeah,
I guess it's like, yeah.
yeah. Eventually, I think you might reach a point of conflict. The one of the reason people like WIMPs is not just that it's not just because of its minimalism. It's because it solves a few other problems. You can ask the question,
Mhm.
well, how come we have this Goldilocks amount of dark matter? WIMPs sort of provide you an answer with that, and this is what people can calculate. Imagine I have a universe with WIMPs, and there's Big Bang, and it cools down. If you do a ballpark calculation, and if you believe in the WIMPs, you kind of get the right amount of dark matter, roughly, in the right ballpark, kind of for free. So people like that, right? But in order to do that, dark matter has to be not too dark, because like because if it's too dark, the dark matter might not destroy them. You might get too much dark matter or not the right amount of dark matter. So you could reconcile that. You can say, hey, dark matter is still quite a bit darker than we thought, but still sort of like a WIMP. But something needs to be modified. It wouldn't be the conventional WIMPs anymore. It has to be a little more exotic. So I mean, you can certainly. There are definitely ways to work it, but yeah, but that will make experiments very, very, very tough.
Hmm. I guess like what we're going to talk about ties nicely with an audience question, which is what theory of dark matter seems most plausible now that WIMPs are out of the running, or allegedly out of the running? Yes, Mikey, I'm going to point to you since you seem to have the answer for this one.
No, I mean, well, I just think it's kind of a loaded. Well, it's a tough answer, but we kind of alluded to this before in terms of the fact that we believe dark matter. There's kind of two options. It's either a really heavy thing that interacts like very weakly through the weak force, so doubly name appropriate, and that seems to fit all of the data, the measurements coming from all these different directions. But the other possibility that just happens to fit all of the data and all the coming from all these different directions is this other extreme where if it's super, super, super light, then it'll actually have like completely different behavior. It'll sort of condense into something like that behaves more like a fluid. And this fluid also has the right properties to match the data in terms of like galactic rotation curves and early universe evolution, abundance, and things like that. So I would say most physicists are hedging their bets on that possibility right now.
Yeah, I think the acronym is WISP, right? I forgot what it stands for. People have all these funny acronyms, but yeah, the other direction is that they can be very, very, very light, as opposed to being like a massive, really heavy particle. But also because of this lesson, I think physicists have looked for more extreme. Maybe extreme is not the right word, but more interesting possibility, right? maybe it's neither. Maybe we just lack imagination with what dark matter is. You know,
Mhm.
like maybe dark matter has many other interesting interactions. Maybe dark matter can form much more interesting objects like planets, or even dark galaxies, or even dark stars and stuff. So these are, I think, sort of the directions of the new generation of research.
Hmm. So what you're saying is like it may not just be heavy or light, or it might be like something very different. Uh, Actually, I don't even. I'm trying to understand like exactly what you mean. Like, doesn't it have to be made up of stuff? So isn't the stuff like heavy or light? Isn't that what we're talking about more than like can form interesting
Yeah,
structures?
I would say the generic picture of dark matter is that it's a particle, and that particle is
Mhm.
very how do I put this? It doesn't like to interact very much. It's very much
Mhm.
like a lone wolf. It doesn't do very much except just float around. You know, they kind of just float around, minding their own business. They don't interact very much, and as such, dark matter will form this very fuzzy structure, a halo. It's like a fuzzy ball, but structureless, more or less. That's the original belief. And
Mhm.
but in this new way of thinking, you know, if you look at ordinary matter, like my hand is very interesting, right? It's not just like a fuzzy blob. My hand has structure.
Mhm.
The planet has structure. The sun has structure. The galaxy has structure. What if dark matter has something like that? But of course, it's dark. We can't see
Mhm.
it. But what if it's there?
Mhm.
Um, so if you embrace that, I think there's a whole new world of possibility. But then the possibilities are almost endless, limitless.
Mhm. And then I guess okay, so then okay, if we were to go with the possibility that dark matter is these like, as Mike was saying, this kind of fluid, it's like really light, light, probably weakly interacting dark matter particles. What would this experiment that's going to be done be invalidated because you would even have more noise? Because there'd be like even weaker neutrinos that can knock things, and you wouldn't be able to tell like what has
These
knocked what
are
or.
usually two separate ideas, though, right? Like the fluid, the idea of the superlight fluid, um, is separate from the idea that dark matter could be have like interesting structure to it. Um, and there are kind of two ways to get around the current constraints. So I just wanted to clear that up, right?
Yeah, I would say let's going back to the experiment. The experiment is measuring exactly what it's measuring. It's trying to see if there are some heavy-ish particles in from the universe just knocking ordinary particles left and right. You know, if dark matter is very
Mhm.
light, it just wouldn't see it because they're not heavy enough to make that kind of impact. Or if there's not enough
Mm.
dark matter, maybe you just haven't waited long enough for this event to happen. So
Yeah,
I
I guess it's
think
just the two possibilities of like so like typically our first assumption when we don't know what dark matter is, we do the typical human thing and assume it's just some monolithic like that's all dark matter. Um, and we assume it interacts in the same way and we don't see it. But one possibility is maybe it's more diverse than that. Maybe there's a bunch of different dark matter sectors and we only have access to like one or two of them. Then you would see these kind of hits a lot less than you would expect. Um, on the other side, if it is this possibility of super light particles, then there's no chance that you're going to see it knocking a nucleus. So you got to find other creative ways to try to tease out its existence. And this actually led to a flurry of interesting ideas using like material science to try to like capture resonances in this fluid and things like that, which we can talk about in another episode. But um, yeah,
That is interesting. I guess where like I guess yeah, where does this like leave us in some sense? Like is um is it only that like you can have very light or very heavy, or have people open up to the possibility of like even in the middle?
I I would say the lesson here is that we shouldn't be too naive about what we don't know. I think you can safely say that the most basic version of the WIMP hypothesis is dead. Like It's clear as day. Like it's dead. But given that, we should just take the experiment at face value and make as little assumption as possible. The experiments show us that we don't have enough heavy-ish particles in the universe to knock some xenon out in a massive vat on the ground. That's what it shows. So that means that dark matter is not dead. Dark matter is very much alive. We know that's what it is. We know it exists. It just means that we need to use our imagination a little bit more, to think more creatively, to find out what it is. And science is hard. You don't always get what you want. And that's just one example out of many.
Yeah. So I know we're almost at time. So wanted to give you guys a chance in our tradition of leading the audience any words of wisdom that dark matter, the lack of WIMPs or non-existence of them have taught you.
This isn't words of wisdom. Maybe it's more just words of depression. We didn't mention this. Like so, we mentioned the most optimistic view. Oh, maybe dark matter isn't totally dark. Maybe it's like neutrinos. Maybe it'll hit a nucleus every once in a while. That's pure. There's no experimental motivation to think that could be true. It's pure blind optimism. What I think it's entirely possible that dark matter is entirely dark. It only interacts gravitationally. And if that's the case, then we're never going to know what it is, which real possibility.
I think I'll be a little more optimistic than that. I don't think we should completely give up just yet.
I'm not saying giving up. I'm just saying like there's a big possibility here, and it's like the elephant in the room that no one talks about.
but it could. I mean, of course, that is a possibility. We may never find it, but I think in science there have been instances where we thought, "Oh, it's hopeless," but then at the end we do make discovery. Although it has become harder and harder in big science, but still we have some examples, maybe not exactly analogous, like gravitational waves. For a while, that people thought we could not see gravitational waves of black holes merging, with some caveats, but hey, we made a discovery. And maybe dark matter is something like that. Who knows? Maybe give it 10 years.
Very optimistic. There's a lot of orders of magnitude. There's a lot of orders of magnitude for where that dark matter portal could be. Yeah. With gravitational waves, we have a sense for where it would be, at least. It was just about getting the technology. But man, if there is a dark matter portal, it could be anywhere between here and the Planck scale.
So I guess this means that Tim, you're more optimistic that we'll find something than Mikey. I guess one question that just came to mind is if you were to formulate a true theory of quantum gravity, it must for sure have dark matter in it. Is that correct?
Ultimately, yes, of course.
Well, no way. No, I mean, like, if you have a framework of quantum gravity, let's say the landscape is true. Like, you have a framework of quantum gravity, but then the dark matter abundance and all that's just details of the landscape, right?
Yeah, I mean, we for the audience.
I guess I am agreeing.
Yeah, I would say see our other episode why quantum gravity can't calculate anything useful. I mean. Ultimately, sure, quantum gravity should have dark matter, but it's not going to tell you much of anything that's useful to our universe. Let's leave it at that.
That's fair. So, so on that note, I want to thank everybody for joining us, and we'll see you all next week.
All right, yeah, see you all.
Bye.